Today I'm going to talk about a metal organic framework called Zn-BPZ-SA that is synthesized by employing tetramethyl 4,4' bipyrazole and squaric acid linkers. This MOF has high stability to water and exceptionally high thermal stability. And the important application of this MOF is for two different mixture separations. Separations of natural gas to produce purified methane. Typically, such mixtures contain 85% methane, 9% ethane, and 3% propane. And we would like to recover methane from this hydrocarbon mixture. Traditionally, this separation is carried out in a sequence of distillation columns. Another separation for which Zn-BPZ-SA is applicable is for separating mixtures from the methanol-to-olefins process. In the methanol-to-olefin process, the reactor products contain a mixture of propylene, C3H6, and ethylene, C2H4. We would like to separate these mixtures to obtain both propylene and ethylene. And Zn-BPZ-SA is capable of undertaking this separation task. The details of the synthesis of this MOF is described in this publication in ACS Materials Letters 2023. It's just available online. This is the DOI for the paper. To demonstrate the separation potential of the products from the methanol to olefin process using Zn-BPZ-SA, experimental studies were carried out for transient breakthroughs of three different mixture compositions. 5,590 mixtures of propylene, ethylene, and argon, which is inert gas used in the experiments. 2,593 of propylene, ethylene, and argon, and 1,990 of propylene, ethylene, and argon. The experimental data at two different temperatures, 273 degree Kelvin and 298 degree Kelvin are shown in the bottom for these three mixtures, and the corresponding transient breakthrough simulations are shown in the top row. What is remarkable is that the transient breakthrough simulations are able to reproduce the experimental data nearly quantitatively. These breakthrough simulations use only the unary isotherms of ethylene, propylene in Zn-BPZ-SA at 273 Kelvin and 298 Kelvin. On the basis of the unary isotherms, the transient breakthroughs of mixtures can be predicted in a manner that corresponds nearly quantitatively with the experimental data. For background on the breakthrough simulations, I refer you to my video, Simulating Breakthroughs in Fixed Beds. The potential of Zn-BPZ-SA for separating mixtures of propane, ethane, and methane are established on the basis of breakthrough experiments shown in the bottom row, and the mixture compositions used in the experiments are 1,2,1780 of propane, ethane, methane, and argon, argon being the inert gas. The left column here are the simulations and experimental data at 273 Kelvin, and the corresponding data as 298 Kelvin are shown in the right hand side. What is important to note is that the breakthrough simulations, using only the unary isotherms as input parameters, are able to quantitatively anticipate the experimental data shown below. And what is also important is to note that from these experiments and simulations, it is demonstrated that 99.95% pure methane can be recovered during the initial stages of the transient breakthroughs. For more details on the simulations of breakthroughs in fixed beds, I refer you to my video presentation on the YouTube channel.